All right, NRF. So we're going to take a look at graphs of relations and functions today, and give you a little bit of kind of the next bit up, I guess we could say. So last time we started out by talking about relations and how relations are basically any link between ordered pairs, I guess, or the link is the ordered pairs that are made. So it's basically any rule for the ordered pair is fine in a relation. Functions are a little more special. Functions, as we took a look at, require you to, for each input that you have, each value that you're given, each domain value, there is one and only one output value or range value that goes along with it. So we're going to see how that kind of meshes in with the idea of graphing. So today, graphs of relations and functions. So first of all, I have a couple of graphs here, and it says, does each graph represent a relation, a function? How can you tell? So even though the dots they're a little small on both of these, I can pull up a highlighter and kind of maybe go along through it. So there's dot here and here and here and here, and I'll just keep clicking the rest of them. And so for this particular graph that we have, the one that's below the first set of text there, Alice's graph, it is temperature in degrees Celsius as the up and down axis, the y-axis if you wish. And then it is time using a 24-hour clock along the other axis. And it starts at 6 o'clock and ends at 4 o'clock. So kind of in the early morning to the early morning the next day. That's fun. And the degrees Celsius at the bottom starts at 0 and it goes up to 18. So how can we tell whether this particular graph is a function or if it's a relation? So we said last time that relations are kind of like any old pairing. So basically any graph is okay. Because there are, in a graph like this, there are two dimensions. So there's two axes, an axis that goes like this, or like this, I guess, and an axis that goes like this. And so because of that, we are going to have two values that correspond to each dot on the graph. So this represents the ordered pair. So one of the values corresponds to one axis and the other value corresponds to the other axis. So for Alice's graph, when we go along at 6 o'clock, which is along the time, is along the x-axis if you wish, or this bottom axis. So at 6 o'clock, we can look up, there is one dot that occurs at 6 o'clock. At 6 o'clock, the temperature is 7 degrees Celsius. All right, moving along. At 8 o'clock, the temperature is 9 degrees Celsius. At 10 o'clock, the temperature is 10 degrees Celsius. At 12 o'clock, the temperature is 14 degrees Celsius. And as you can tell, it kind of has this interesting curve to it, where it kind of goes up nicely here, and then it goes up quick, and then it falls down quick, and kind of levels off and starts warming back up on the next day. So the idea is that we don't really care about the trend that much. What we care about is whether this thing is a relation or a function. So I'm going to say out loud what a function is. So for each and every value that is in the domain, there's a domain value. If we carefully kind of trace with our eyes, each one of these values actually corresponds to a point. So for this particular graph, which doesn't have to be the case, each of the labeled breaking up of the x-axis actually does correspond to a point. So for each of the values in the domain, there is only one value in the range. So for each value in the domain, there is a 6. There's only one temperature that goes along with 6. There's only one temperature that goes along with 8 for the time. There's only one temperature that goes along with 10 o'clock for the time. So this, if we keep going along, only has one and only one value on the temperature axis for each of the time axes values. So this one is definitely a function. because there are no values, I guess you could say, where it breaks that rule of having two y values for one particular x value. Now, here's Joe's graph over here. So Joe's graph is looking at something a little bit different, also during the same time window. So we're going from, again, 6 to 4 on a 24-hour clock. But this one says number of species is what's labeled along the y-axis. So it's graphing something different. And again, we have in this particular spot individual dots that are plotted along here, and it looks like he also recorded the information on these 2-hour intervals and wrote it down on his graph. So each one of these times has one and exactly one value along the y-axis corresponding to it. This one, is also a function, because it follows that same rule. There is only one y value for each of these x values that exist down here. Now, I'm saying x and y because that's like the generic axes that we sometimes give them. It would be very reasonable for this person to say that it was t versus n, or s for species, and so you could have a time axis and a species axis. Same thing over here. A little t and big T sometimes. That one's a little bit more confusing. Sometimes we use that in physics. So little t for time and a larger T for temperature or chemistry. So in these particular situations, they are both functions. They're definitely relations automatically because they're pairing up information on one axis and the other. So each dot that's there represents an ordered pair. But they are also both functions as well. So now I'll draw your attention to what's going on down here, which is which of these graphs should have the data points connected. Now, this is an interesting question because neither of them are given with the data points connected. And the problem is that, I guess if we were to think of connecting them, most of us would probably break out a ruler and start playing connect the dots. Now, I'm not going to get into whether that makes the most sense here or not, because it actually probably doesn't, because it doesn't look like these would be linear changes, even if connecting them would be appropriate. Now, in the case of temperature changing during the day, temperature changes smoothly. So we're not going to get into the nitty-gritty of what makes heat and temperature, but for instrumentation, we're going to say that temperature changes smoothly. So you can't get from, for instance, 7 degrees all the way up to 9 degrees without going through 8. Also without going through 8.1. Also without going through 8.02. So each one of those values is going to, at some time between 6 o'clock and 8 o'clock, are going to occur. There's actually something we talk about way down the road in grade 12 known as the intermediate value theorem, which basically says, hey, if you're at 7 and you're at 9 and it's a continuous function, which this one would be, then you can guarantee that all the values in there happen at least once, no matter how they're connected. So this one here, it would probably make sense that there is some sort of connection. Now, whether the connection is kind of linear looking or more curved like I'm doing is hard to kind of make too much of an argument for, because we're not given the data that would allow us to know that. However, since these represent a continuous set of information where there should be numbers in the middle, then it would make sense that these could be represented using connected data points. So something like this would be appropriate. In Joe's graph, Joe is representing a number of species. This one's a little more wonky. And without getting too argumentative over whether you can have half of a species or a quarter of a species, I'm going to say no. So from our math point of view, we're going to say that you either have a whole species or you do not have any species. So when you record that there's 25 here and that there are probably 24, looks like, if I kind of skim with my eyes, at the 8 o'clock mark, I'm not going to in between have 24.5 species. Now, could there have been a dot between 8 and 10 where there was something like 22 species? Yeah, there could have been. Could there also have been instantaneously 4 species that died, I guess? I don't know what we're talking about here, but that died between the 8 o'clock and 10 o'clock hours? Yeah, you could have had them all perish right at 10, I suppose. That information is not a part of this graph, but it also is not unrealistic that that's the case. So if we try to connect these two things, that doesn't really mean, or these dots, that doesn't really mean what we think it means over here. That, hey, those temperatures definitely have to happen and exist, all of them. Over here, there never has to be a time where there are exactly 21 species. You could instantaneously go from that happen at the same time one and jump to another, and so because of that, and you don't want to represent even if there was a step there, they would be individual points that are stepping. You wouldn't get things like 24.9 and 24.8 and 24.89 and 24.88. Those just aren't going to be an appropriate marking for the number of species. So we're going to decide when things should be connected and when things shouldn't be connected by using a bit of logic and I would say common sense, but that may be a little bit unfair. So you kind of just think your way through it and use some logic to assess whether you think a graph should be connected or not. We'll see lots of examples of these. So a lot going on in this particular screen, so I'll kind of take you through. I'm going to start over here. It says a sugar cube has a volume of 5 centimeters cubed and a mass of 4 grams. Graph the mass of sugar as a function of the number of sugar cubes from 0 to 5 sugar cubes. So I'm going to, with you right now, let's just make a set of axes. So I'm going to make this one and this one. And I'm going to, I wish I could write on it. I probably should just do it on my iPad, but I'm going to go against that for a moment. So I'm going to put a 0 there, and I'm going to just talk my way through it then. So what I'm going to say this time is that every 2 things here is going to be 1 sugar cube. So that's 0, 1, 2, 3, 4, 5. And I'm going to maybe just label that as being a 5. And then the mass, since I know for every 5, each one of those sugar cubes is 4 grams of mass, then it would be something like, well, let me just do it nicely as 4, and then 8, and then 12, 16, and 20. So we'll go up to 20, and we would get at 1 sugar cube, there is exactly 4 grams. And then at 2 sugar cubes, there are 8 grams. At 3 sugar cubes, there are 12, 16 at 4, and 20 at 5. Now, the question would be, should I take this and put a nice straight line through it? That's a real thick line. But should I put a nice straight line through it, or should I leave them unconnected? And the other thing is, how did I determine to put the 0, 1, 2, 3, 4, 5 on this axis and the numbers from 0 to 20 on this axis? Well, okay, so we're going to answer those questions. So first off, I'm going to talk about the connectedness of this particular graph. So I am going to leave this as being unconnected because in this particular description that we have over here, it is a function of the number of sugar cubes, and it doesn't give us any indication that we're allowed to use partial sugar cubes or break them up. If that's the case, you can choose 1, 2, 3, 4, or 5 sugar cubes. And so what we would see is that in this particular example, we would have these nice, yellow was a kind of a crummy thing, 5 nice points that would be all along there that we can see. So that's great. How did I decide what to put on the x-axis and what to put on the y-axis? last time we had a little bit of a discussion about the independent and dependent variables. So I'm going to write this down. The x-axis is the one we are going to generally and as a rule, we are going to select for the x-axis the independent variable. And then the y-axis, so my x-axis is my side to side, my y-axis is my up and down. We are going to select for that instead the dependent variable. So, does the mass of sugar depend on the number of cubes that you pick, or does the number of cubes that you pick depend on the mass of sugar that you have? Again, you could probably talk your way into a bit of a pickle with those, but think about which one sounds a little more logically smooth. So if you have a particular mass of sugar, that mass was dependent on how many cubes you picked out. If you have a particular number of cubes, you might say, well, I was looking at a recipe and I needed a certain mass, so it was dependent on that. Again, I understand that, but the direct relationship here is that the mass of sugar that you have is going to change based on the number of cubes that you select. So your number of cubes is going to be your independent variable, and your mass is going to be your dependent variable. So this was my number of cubes, and this was my mass of those sugar cubes. Again, unconnected because you have individual cubes of sugar. The other thing here, and I should label it as I go, I'm kind of running out of room. 5 cubic centimeters of loose sugar also has a mass of 4 grams. Graph the mass of sugar as a function of volume of sugar from 0 to 25 centimeters. Oh, I guess I just went back, didn't go back through and proofread that one. Centimeters cube of loose sugar. All right, so let's go ahead and do that. And again, we'll have some axes here. And I'm going to take the same variables on the same axes, except for this time, I'm not going to actually have a number of sugar cubes. Instead, I have a volume of loose sugar. And the mass of sugar that I get is going to be dependent on the volume of loose sugar that I select. So this time, as I go along my sugar axis here, I'm going to have 5 and then 10 and 15, 20 and 25 cubic centimeters of loose sugar. And going up this axis is actually going to be the same as last time. So I'll have 4, 8, 12, 20. 16, 20 as the mass. So mass in grams, and down here this is going to be centimeters cubed of loose sugar. So again, I'm going to take and put points down here. It says for 5 cubic centimeters of loose sugar, so 5 would be this here, is going to have 4. And so here, 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 and here. So we would get, just like last time, actually, a set of 5 points at exactly the same spots. So the amount of mass that you get actually is, whether it's in cube form or whether it's loose, it shouldn't really matter because it's just whether it's holding together or not. So we would get the exact same graph. Okay, so what's the point of this particular slide? What are we trying to show? So the idea is that this one, because they have to be in individual cubes, you are stuck with those individual cubes. Here, it would be entirely okay for you to say, oh, well, what if you wanted to measure out 21 cubic centimeters of sugar? That would be okay. What if you wanted to measure out 21.5 cubic centimeters? That would be okay too. So it would be an appropriate thing to connect your values in this particular case. And since we're going to see something a little bit later on that's going to talk about linear functions, it would be appropriate to connect them with a straight line this particular time because of the linear relationship between the loose sugar volume and the loose sugar mass. So again, dependent and independent variables, it's going to be whatever your kind of is the thing that you're counting up is your dependent variable, and then whatever's being affected by that counting up is your dependent variable. And x-axis is your independent, and your y-axis is your dependent variables. All right, so are there restrictions on the domain and range? Okay, so what this means is there a particular way that we need to describe this domain and range because of the connectedness? And secondly, because of the values that we're allowed to start with and go up to. So we're told here that it would not make sense to talk about negative cubes of sugar. Just doesn't make sense. Same thing with having like -3 centimeters cubed of sugar, but it just isn't something that you really care about. So what we're going to say is that 0 is the lowest amount of sugar that you can select. So if I'm talking about the domain, so I'm going to do the top graph first. So the domain. First of all, that is an unconnected graph. How many data points are there that are viable or actually existing, a part of the set, in our graph? There are 5. I'm gonna count 0. You know what? I probably should have put that those would have a nice little highlighted dot bloop here and down there with the pink one there, because 0 is viable. It's okay to not select any sugar. All right, and it says over here 2. So we have 1, 2, 3, 4, 5, 6 actually. Now, when I go to write my domain, I'm going to do this in, if you choose to follow the way that the textbook does it, that's okay. The textbook does it in a little bit of a relaxed way, I'm going to say. I'm going to use something called set builder's notation. In set builder's notation, instead of me just listing out the values, I'm going to put some little things around them. So there is a curly brace here to represent that I'm talking about a set. So the domain is the set of numbers that involves 0, 1, 2, 3, 4, and 5. No other numbers are allowed to be part of the domain, and so that is the full domain. It's restricted because I can't go down past 0 and I can't go up past 5. And it's also restricted because I'm only allowing those whole number or natural number values. I'm not actually allowing real numbers or rational numbers or irrational numbers. So rational, irrational, therefore all real. All right, so my domain is just going to be 0, 1, 2, 3, 4, 5. Typically, you'll see that sets are ordered. So I started with 0 and went up to 5. And that's really pretty typical. They do not have to correspond. Now, these ones will because it's a linear relationship, so everything will kind of line up really nicely between the domain and range. That's not a requirement. So these are two separate sets, even though I'm writing them right underneath each other. The range is going to be 0, 1, 2, 3, 4, 5. So that range being 0, 1, 2, 3, 4, 5. Oh, nope. I'm counting grid lines. Let's try that again. It's because my graph is not labeled very well. So it's 0, 4, 8, 12, 16, 20. So 0, 4, 8, 12, 16, 20. Well, I'm not going to go back and fix that, but sorry about that. So 0, 4, 8, 12, 16, and 20. So those are going to be my range values. So I have my set of my domain, and I have my set of my range. They are restricted due to the number of the values that are allowed, but they're also restricted due to the fact that we are choosing only a whole number values to represent the number of sugar cubes, and therefore there's a discrete number of values that correspond to that. So the bottom graph. So for the bottom graph, I'm going to have a domain where I start a set by using my squiggly brackets. And this time it's different because it's the line, really. Any of the values between 0 and 25 cubic centimeters of loose sugar are allowed. How do I write that? If I use x to be the variable that is going to represent my domain, then I would have, and you know what, I'm going to do the full-blown deal. So x is going to be what represents my domain, and then I'm going to write this vertical line. This vertical line is a mathematical symbol that means such that. So it's going to be, I'm starting a set, my set contains x's in it, such that, and now we list the rules for x. X has to be a value that is between 0 and 25, but it's also allowed to be equal to 0 and 25. So I'm going to put the greater than or equal to symbol, less than or equal to symbol, less than or equal to symbol. And then I'm going to also list another rule. I'm going to say that x has to be a part of the real number system. Now, as a side note, what your textbook would do for this right now, which is okay, and you can follow along with this too, is just saying this without any of the other notation. So it would say 0 is less than x is less than 0 is less than or equal to x, which is less than or equal to 25. And it wouldn't have the beginning curly brace x such that, and it wouldn't say that x has to be a real number afterwards. That's okay. This is a much quicker way to write a very similar thing, and it just saves you a little bit of time. In the long run, this way is nicer. The other way that I have written down here, so up here, but it's more clear. It's okay though. Choose to do it either way you wish for the time being. So for your range, I'm going to say that they're y values such that, and the mass of the sugar that we can have is going to be all of values between 0 and again, I'm kind of counting up here. For 5, it would be 20. And so over here, it's again 5, 20. So there would be 20 grams up at the top end there, where y is an element of real numbers. And I put my little curly brace there, kind of ran out of room there. All right, so that would be my domain, that would be my range, and yes, there are restrictions on them. So these rules that I've written here, these rules are restrictions that tell you what you're allowed to do and what you're not allowed to do. So my domain for the top graph is restricted to be only the numbers 0, 1, 2, 3, 4, 5. My range is only allowed to be the numbers 0, 4, 8, 12, 16, 20. For my bottom graph, I could have anything from 0 to 25 as a part of my domain, and I'm allowed to have everything from 0 to 20 as a part of my range. So you'll see that there are very different ways to write domain and ranges. Sometimes they're a list of numbers or even words, but we're going to mostly concentrate on numbers. You're going to see that they're a list of numbers. Sometimes you see that they're rules that involve less than, greater than, or less than or equal to, or greater than or equal to signs. And that will depend on whether you have connected or unconnected graphs. I'm actually going to take a minute here because I don't think I have a slide for it. And I'll just off to the side over there, I'm going to write down continuous data versus discrete data. Continuous data is connected, and it means that there is a reason to connect it. Otherwise, you shouldn't really do that. Discrete data is unconnected. Again, because there is a reason why this data is and should be unconnected. So continuous data is going to look like this. Discrete data is going to look like this for a similar situation. And because of that, in a continuous data domain or range, you're going to describe it using rules, because there's no way you want to list the infinite number of points in that line, because that's how many there are. even if it has two ends on it, there is an infinite number of points in the middle, and listing them all is not a great idea. In something like this, it's actually more complicated to list the rule than it is to actually list the 4 points. So you would say, if it was 0, 1, 2, 3, then you list 0, 1, 2, 3, instead of saying, well, it's all the numbers between 0 and 3, as long as you're making sure there are only whole numbers involved. Well, why didn't you just say 0, 1, 2, 3? So we do. Generally, for the sets of discrete data that we'll be working with, it's easier to write it down as a list as opposed to rules. So you're going to see things like x between 0 and 10, or maybe in this case 0, 1, 2, 3. So the way you write that with notation is going to look a little different. Actually, if I'm doing the same thing here and here, where I kind of ignore the squiggly notation, the first one, then I would just list them 0, 1, 2, 3. All right, so that's a little side note, but an important one. So we'll keep going. So we can represent the function that associates every whole number with its double different ways. So one of the things that I want you to realize is that when we have some sort of relationship between something and something else, we can use tables, we can use graphs, we could use other graphical arrangements. So you could do, for instance, like one of those arrow diagrams where you have the bubbles and you draw arrows between them. That would be another okay way to do these. So if I am just to use a table, let's say I start with the number 0, just to keep things simple. What's the double of 0? Well, it's 0. What's the double of 1? 2. What's the double of 2? 4. What's the double of 3? 6. We could keep going, but that's fine. I could also use a graph to show this. So 0's double is 0. And of course, let me do this without making a complete mess. So let me hold that there. And let me hold that there. So at 0, I would have 0. At 1, I have 2. At 2, I have 4. At 3, I have 6. So if I go along and label these axes a little better. So this is at 1, 2, and 3. And this is 2, 4, and 6. Now, this particular example, it says that we are doing this for whole numbers. I'm not missing anything then. Actually, you could argue, since I said whole numbers, not natural numbers, I shouldn't have 0. So that's kind of crappy. But I'll get rid of that. So we would have 1 doubled is 2, 2 doubled is 4, and 3 doubled is 6. So I've listed it both in a table. And I've also listed it over here as a graph. And so in table form or graph form, where both of these are representing the same relationship, which is a function in each one of these. All right, so that's just, again, it's just saying that we can represent these in different ways. We could also say 1, 2, 3, 2, 4, 6. It's a little messy, but get the idea. So it's kind of that same sort of thing that we looked at last time with the arrow diagrams. All right, so a relation that is not a function has 2 or more ordered pairs with the same coordinate. A function's ordered pairs all have different first coordinates. So what that means is we can skim along and say, only 1, -2, only 1, -1, only 1, 0. 1, 2, 3, 1's not a function. So that is a relation, but it's not a function. Only 1, only 1, only 1, only 1, only 1, only 1. Great, that is a function. So how do we tell the difference really quickly? Well, you can skim, but one of the nice things that we can do is skim calling a vertical line test into play. So a vertical line test is if you take your hand or you take an object that is nice and vertical, and you basically just, well, I'm going to do it from this side because that makes more sense for you. You're basically just going to take it and you're going to skim it across your diagram. So if when you skim it across the graph that you're looking at, you get that it cuts through every single point. It only cuts through one point at a time. Cutting through 1 point, that's okay. 1 point, that's okay. 1 point, that's okay. 3 points, bang. All right, not a function. This one over here, 1, 1, 1, 1, 1, 1, good. So you are basically taking this idea of a vertical line and you're skimming it across your graph in order to tell whether this thing is a function or not. So I actually went ahead and talked a little bit about domain and range before we got to that. So I'm going to cut that for now, except for I'm going to do, just really briefly, a few little diagrams of things that we're going to do vertical line test on. So I have my vertical line, and I'm going to take that vertical line. Oh, is it going to let me? No, it's not going to let me select that like that. That line is not even vertical. Ooh, rough. All right, so I have my vertical line, and then I go skim it across. Ew, big fail. All along here is almost a fail. The only place where it's not a fail is at the very beginning. It only cuts one value. In the very end, it only cuts one value. So we pass a vertical line across that and use that idea of a vertical line test to tell very quickly whether the picture we're looking at is a function or not a function. So that's good. That's my introduction to graphing functions and relations, or interpreting graphs of functions and relations, talking about domain and range, and going from there. So I hope you're doing well, and hope to hear from you soon as well. Take care.